No, you do not have early dismissal today. All right, you said number 27, right? Okay, number 27. You have early dismissal tomorrow, but today is regular bells. All right, number 27, reflect triangle CSR over the y-axis, graph and label C prime, S prime, R prime, and state the coordinates of C prime, S prime, R prime. So if we're going to reflect over the y-axis, sorry, there we go. X is going to change sign. Since we're reflecting over the y-axis, the y coordinates will stay the same. So I'm going to look at each of these ordered pairs. In C, we have negative 4, 1. So C prime, we change the sign of X, that's 4, but the y stays the same. Then we come over here to S, that's at negative 3, 3. So S prime, we change the sign on X, we leave y alone. And then R, negative 1, 1, we change the sign on the X, we leave y the same. And then we're going to go and plot those points. 4, 1. That is my C prime. 3, 3. That is my S prime. And 1, 1 is R prime. And then we trace in that triangle shape. All right, then part B of this says translate C prime, S prime, R prime using, and then it has these angle brackets. These are not parentheses. These are angled brackets. The first number inside the angle bracket tells you how far left or right to go. Because this is positive, we're going to go to the right 2. The second number in the angle brackets tells you how far up or down to go. Since it's a negative, we're going to go down 3. So you can do one of two things at this point. You can either count on the graph, or you can use these ordered pairs. If I'm going to go right 2, that's a positive 2, so I would add 2 to the x's. If I want to go down 3, that's a negative 3, so I would subtract 3 from the y's. So C double prime would be 6, negative 2. 6 because that's 4 plus 2. Negative 2 because that's 1 minus 3. Yep. So we're going to take this point right here. We're going to count to the right 2. 1, 2, and down. 1, 2, 3. Right here. There's C prime. Oh, sorry, to the right. My bad. You're right. To the right 2. I'm having a Wednesday, sorry. Even though it's only Tuesday. Right 2 and down 3. There we go. There's C prime. And that's 1, 2, 3, 4, 5, 6, negative 2. We do the same thing with S. Add 2 to the x, subtract 3 from the y, so that should put us at 5, 0. I can come over here to the graph and I can count that, so I'm going to take S prime. I'm going to go to the right 2 and down 3. That's going to be right here. There's my S prime. And then R prime, add 2 to the x, subtract 3 from the y, so that puts me at 3, negative 2. Over to the graph, from R prime, we're going to count 2 to the right and down 1, 2, 3, right here. Sorry, these should be double primes, not single primes, because we're moving our single prime. Thank you. Nope, thank you. All right. What else would you guys like to see from the review? Thank you, Sarah. Any other problems off the review that you guys would like to see me work through? Pick one out. I'll happily do it. Did you say which one? 26? Absolutely. All right, so we are supposed to find the vector, so we're going to write something that has angle brackets. The first one that we're going to write takes us from triangle 1 to triangle 2. So I'm going to pick out a point on triangle 1, like I'm going to pick this corner. I could pick any of the corners, but I'm going to pick that one. And I find the corresponding corner on triangle 2. That would be this one right here. And then I'm going to count how far, left, right, up, or down. To go from triangle 1 to triangle 2, I don't need to go left or right at all. That's always what the first number tells me. Since I'm not going left or right at all, it is a 0 there. What'd you say? It's an angle bracket, yep. It has to be inside an angle bracket when we're talking about movement. All right, and then to get from triangle 1 to triangle 2, I didn't go left or right at all, but I do go up 1, 2, 3, 4, 5. So the second part of my angle bracket would be a positive 5, because we went up 5. If you go down, it's going to be a negative. If you go up, it's a positive. With that first number inside the angle bracket, the one that describes our left-right movement, if we go to the right, it'll be positive. If we go to the left, it'll be negative. Part B, we're going to start with triangle 2, where we just left off, and we're going to move it so that it becomes triangle 3. So again, I'm going to pick out one of the vertices, one of the corners. I'm going to pick out, say, the top one this time. It doesn't matter which one I pick. I'm going to find the corresponding corner, the corresponding vertex on the other triangle. So like right here. And to get from triangle 2 to triangle 3, I move to the right 1, 2, 3, 4, 5, 6, 7, 8. So the first number inside my angle brackets is going to be a positive 8, because we went to the right 8. And that gets me all the way to triangle 3. I don't have to move up or down at all. So the second number inside the angle brackets is going to be a 0, because there's no up, down. Yep.
So if you started from like the triangle 2, you start from the bottom left, would it be 9 then?
Nope. Nope. Because you have to go to the corresponding corner on the other triangle. So if I started right here, I would have to go to right here. And that would be 1, 2, 3, 4, 5, 6, 7, 8. It's the same movement no matter which corner you start from. Yes?
Is it always up, down the numerator and right, left in the denominator?
For,
Like when you're like.
so we don't have numerators or denominators here. That's why I'm asking. That's your slope, and that's not what we're doing here. This is not slope. These are translation vectors. Of slope? Let me finish up part C, and then we'll go look at something. All right, part C, we're going to start from triangle 3, and we want to end at triangle 1. So I'm starting here, and we're ending down here. So basically, I'm doing what I just did, but in reverse. So if I start at triangle 3, to get down to triangle 1, I would have to go this way. I would have to go left 8, and then I would have to go down 5. That's the reverse of what we just said. But in my angle brackets, since I have to move to the left, that is a negative 8. And then I have to move down 5. So that would be a negative 5. So Kemi, slope and translation vectors are both describing movement, but slope is describing how you move to find the next point in a line, and slope is only for lines. Here we don't have lines, we have triangles. So if I want to move a triangle, we have to use a translation vector, and it moves the entire shape. Slope just tells me my rate of change on my line. It's not the line moving. This is like picking up and moving an entire object. Does that make a little bit more sense?
Okay, so like these shapes, like they stay the same, like they stay the same like shape.
So a translation vector is literally doing something like that with my shape. Slope is telling me my rate of change. It's describing as the x part of the equation changes, how does that affect the y part of the equation? How much do I go up or down based on changes that happen with my x variable, if my x gets bigger or smaller. But a line is infinite, it goes forever, so my line is not moving. It's just telling me how I need to move to find the next point on the line. Does that make a little bit of sense?
Yeah, why is orange 0? Oh, because it didn't move left.
Didn't move left or right at all. That first number in the translation vector always tells you how far left or right you're moving.
Okay.
The second number in the translation vector tells you how far up or down you've moved your object. All right. What else would you guys like to see? Any other problems that you guys would like me to go over? Yes. Yes. If you switch the numbers around, guys, that's a really, really good question. If you switch the numbers around, would it be wrong? Yes. Because the first number in the translation vector is always telling you how far left or right you move. So if you switch the numbers around, you're going left or right a different amount. If you were going up 6 and right 6, then it doesn't matter because you're moving in the positive direction and you're moving the same amount. But if you're not going up or down the same amount that you're going left or right, or you're moving in the negative direction for one and the positive direction for the other, it absolutely does matter which one goes where.
So these are medians? Those lines are medians?
Those are medians, yes. Yep. Is there anything else that you guys would like to see off of the review? All right, so number 24. Find the coordinates of B prime for each transformation described. This is all Module 4 stuff. Okay, so when we reflect across the line y equals x, our rule for that is that we switch the x and the y coordinates. So I'm going to take 5, negative 2. We're going to switch them around. So that would become negative 2, 5. Rotating 90 degrees clockwise about the origin. So when we go 90 degrees, we're going to switch. And then we have to match our signs. To the correct quadrant. All right, so I'm going to draw a quick little sketch. Our point B is at 5, negative 2, so B is somewhere down here in the 4th quadrant. We're going to go 90 degrees clockwise, so that's going to move me into this quadrant over here. That is my 3rd quadrant. That is a negative, negative quadrant. The x's are negative over there, and the y's are negative over there. So I'm going to switch the 5 and the negative 2 around, and they both need to be negative because they're going to land in that 3rd quadrant. Part C, we're going to do the same thing, except this time we're going counterclockwise. So we're still going to switch and match our signs. To the quadrant that we land in. So I'm going to do another quick sketch. Again, 5, -2 is down here. Here's my point B. Counterclockwise, the opposite direction of a clock, would send me up here into quadrant 1, which is a positive quadrant. So I'm switching the 5 and the -2 around, and everybody ends up positive in the end because we're landing in a positive quadrant. For the last one, we're going 180 degrees. You do not switch the order. But you do match your signs. To the quadrant that we land in. All right, so one more time. Point B is over here in the third quadrant. Notice it doesn't say whether I'm going clockwise or counterclockwise, because if I'm going halfway around the clock, I'm going to land in the same spot either way. 180 degrees. Or I could go this way, 180 degrees. Either way, I land over here in the second quadrant. Second quadrant has negative x's and positive y's. So I'm going to leave the 5 and the -2 in the same order that they're in, but I have to make sure that the x part comes out negative, so that 5 has to become a -5. And the y part of the ordered pair has to come out positive, so that -2 is going to switch to become a +2. All right. What else would you guys like to see?
I have a question.
Yep.
So when you're like, so remember, okay, so like, you know, so when you're doing substitution property, but instead of it just being substitution property, there's a congruent symbol which translates property, right?
That's right. When you replace something and there's a congruence instead of an equal sign, that has to be our transitive property. All right, number 29. In the diagram, the measurement of angle A is 2x. So I'm going to put 2x degrees on here. The measurement of angle C is 20 degrees. And the measurement of angle B is 4x minus 10 degrees. We're going to need to use our exterior angle theorem. Exterior angle theorem. What the exterior angle theorem says is that the exterior angle, or the measurement of the exterior angle, is equal to the sum of the two remote interior angles. So when I'm looking at this triangle here, my exterior angle would be angle B, because that's on the outside of the triangle. To be a remote interior angle, it cannot be touching my exterior angle. So this angle right here that it would form a linear pair with, that's not a remote interior. These two angles right here, because they don't touch angle B, but they are inside my triangle, are remote interior angles. So to set up this equation, I'm going to have the measurement of angle B, that's my exterior angle, is equal to the sum of my two remote interior angles. So the measurement of angle A plus the measurement of angle C. In the place of angle B, we're going to put 4x minus 10. In the place of angle A, I'm going to put 2x. And in the place of angle C, we're going to put 20. And now we're going to solve this for x. So the first thing I'm going to do if I'm going to solve this for x is get my x's to the same side. So I'm going to subtract 2x from both sides. Oh, sorry, I put my cross through the wrong thing. It's going to cancel out with the 2, not with the 4. 4x minus 2x gives me 2x minus 10 equals 20. Then I'm going to add 10 to both sides. So I get 2x equals 30. Swing my work around because I ran out of room. And then I divide both sides by 2. And 30 divided by 2 gives me what? 15. So x is 15. Oh my goodness. That is one of the things they asked me to find. So I can put that in. Now I need to also find the measurements of angle A and B. Well, the measurement of angle A was 2x. So I have 2 times 15. And 2 times 15 would give me how much? 30. So the measurement of angle A is 30 degrees. And then the measurement of angle B was 4x minus 10. So I do 4 times 15 minus 10. What is 4 times 15? So 60 minus 10 would give me 50. Remember when we said at the beginning of this problem that the sum of the two remote interior angles is equal to the exterior? Well, this one up here is 20. We said that angle A was 30. 20 plus 30 gives me 50. And that's how big my exterior angle, angle B, is. It's 50 degrees. Just a little bit more than 10 more minutes. It's time for 2 or 3 more problems, depending on the problems.
What would you put like the equations and stuff?
On the cheat sheet, I would make sure to have the formulas. So formulas that I would make sure to have. Hold on, I made a list for somebody the other day and then I took a picture of it so that I had this. I would have midpoint formula, slope formula, distance, circumference and area of a circle, point slope form, slope intercept form, rules for reflections and rotations, triangle sum theorem, exterior angles theorem that we just went over, triangle congruence postulates, our rules for centroid and median, and then how to find the lower and upper boundaries for a triangle. Those are the things that I would have. Do you want me to kind of list those out?
Yeah.
Okay, yes.
I was gonna ask if you could specifically list out the lower and upper bound.
Yep, or how to find that rather.
Is that actually subtract lower bound, add upper bound?
Kind of, yeah. You add for your upper bound and you subtract for your lower bound. Okay, so you need to know midpoint formula. For midpoint, capital M to stand for midpoint equals, and then we've got a big set of parentheses with two fractions inside.
Do you have to add the M inside? Or like the M on the outside?
Do you have to have the M on the outside? That's what stands for midpoint. So how you find the midpoint is what comes after the equal sign. All right, so there's our midpoint formula. Slope. Slope usually gets represented by a lowercase m, not an uppercase m. I don't know why math recycles that stuff. To find slope, y2 minus y1 over x2 minus x1. That numerator is your rise. The denominator is your run. Distance formula. So distance, lowercase d, is equal to, we subtract our x's, x2 minus x1, and we square it. Plus, and then we do the same thing with our y's, y2 minus y1, and we square that. After we add them together, we take the square root of the whole thing. That is the long one, yes. Circumference of a circle, C equals 2 pi r. Area of a circle is A equals pi r squared. Slope-intercept form. Y equals mx plus b, where this lowercase m is your slope, which we saw up above how to find, and b is the y-intercept. We also learned point slope form. Y minus y1 equals m, and then parentheses x minus x1. Again, m is your slope. X1 and y1 are from a point or an ordered pair that you're given. You do not replace the x and the y, you replace the x1 and y1. All right, rules for transformations. Number 6. Those are all segment addition postulate. Just because they have subtraction in them does not mean that they're not segment addition postulate. The segment addition postulate means that you have two smaller segments that have been put together to make the larger segment, which you can also then take backwards and take a larger segment, take away a smaller segment, and be left with another smaller segment. But it still has to do with three segments where the points are collinear, where they're all on a line together. Good question. All right, so for our translations, we're going to shift left or right, and then up or down. The left right is the X part. The up down is the Y part. For reflections, if it's over the x-axis, x stays the same, y changes signs. If it's over the y-axis, then x changes signs. And y stays the same. If it's over the line y equals x, you're going to switch your x and y. If it's over the line y equals negative x, you're going to switch your x and y. And change both signs. For rotations, (90 degrees clockwise, or counterclockwise. You will rotate, so you're going to switch x and y and match the signs to the quadrant. And that is for 270 or 90, clockwise or counterclockwise. For 180, doesn't matter whether it's clockwise or counterclockwise. Same order, so you do not switch x and y, but you do match your signs. To whatever quadrant you've landed in. Triangle sum theorem. All the angles in a triangle add to 180. Exterior angle theorem. The exterior angle is equal to the sum of the two remote interior angles. For centroids and medians, centroid to midpoint, that gets described as an X relationship. Centroid to vertex, is 2x, and the whole median is 3x. And then on our triangles, upper and lower bounds, if we know two sides of a triangle, my upper bound is going to be when I take those two sides and add them together. My lower bound is when I take those two sides and subtract them. So it couldn't be smaller than the difference, and it can't be bigger than the sum. Let's see if I have enough room to add that. Don't know if I do. Lost part of my x there, though. We'll carve out a little space in the middle here. Third side of triangle. Lower bound, difference of the two sides. Upper bound, sum of two sides. That is everything that I could think of formula-wise that we have talked about this semester. Obviously, some of those aren't formulas, but they are rules that govern those transformations.